Welcome to Lecture 20. This is part of Module 3, the second in the series, focusing on metals used in additive manufacturing. In this lecture, we shall begin from that map that we saw, different kinds of metals that are used in all of manufacturing, and prioritize those that are specifically used for fabrication of components by 3D printing. To quickly review, we saw that powders come in all kinds of shapes depending upon the powder synthesis method. It can occur in a wide range of size distributions. They have different levels of actual density and packing density, different surface area. They have both internal porosity as well as they create porous structures when components are created out of them by sintering or melting. Chemical composition affects processes, affects properties, and are subject to change during process conditions. In addition to the chemical composition, the crystal structure, the phases can also change based on process conditions. We looked at sintering as a common route traditionally used for fabricating dense components out of powder metals. Sintering approaches are used after shape creation for a few 3D printing technologies such as selective laser sintering, fused filament fabrication of metal polymer composites, photolithography applications using metal powders, and binder jetting. So in sintering, you're really talking about a thermal treatment as we reviewed to bond particles, improve strength, create densification, and improve other properties as well. So the driving force of sintering we reviewed in the previous class, talking about the effect of atoms on a curved surface that is highly strained, few nearest neighbors. There is a driving force of minimizing of surface energy, be able to drive atomic motion across powder particles. There are several mechanisms by which this atomic motion can be achieved during sintering. They're all diffusion processes typically. That diffusion can be along the grain boundary. They can be through the bulk of the volume. It can be through surface diffusion across this. It can be evaporation and condensation to grow the neck around here. The pore shrinkage and the surface tension that stabilizes these pores is another aspect that needs to get considered. Grain boundaries, plastic flow for bulk diffusion are other ways in which things can happen. In addition to solid state sintering, as is shown over here, we also have liquid phase sintering where you have a mixture of metal particles, one having a lower melting point compared to the others. So when the dark powders shown undergo melting, they can, by capillary action, pull the particles together. In addition, that liquid phase can enhance diffusion of atoms in the solid particles and lead to solution reprecipitation. Final densification is observed. Materials that undergo liquid phase sintering include tungsten heavy alloys, refractory metals with very high melting points. Here's an example of a projectile formed by processing tungsten heavy alloys, the liquid phase being copper or iron nickel components. Here's an example for a tungsten heavy alloy, the microstructure, the liquid phase being the lighter regions over here, and the solid phase being the refractory metal with a little bit of the liquid also dissolved into the solid particles. Cutting tools in the form of cemented carbides are also formed this way. Tungsten carbide cobalt is a good example. We will look at tungsten carbides in the module 4 while looking at ceramic system. So the lighter regions are the cobalt rich regions. The darker regions with the sharp edges are the carbide rich regions. Sintering is a time and temperature driven process. So here's a plot of time on the y-axis versus temperature on the x-axis. It is clear that if for lower temperatures and lower times you would end up having lower density products. On the other hand, at higher temperatures for longer times you would have extensive grain growth in the microstructure. You could also have distortion occurring. So it is reasonable to assume that there is an optimum window, referring to a sintering window, that provides a balance between finer grain sizes, higher densification, and shorter process times and lower energy. This changes according to the type of the materials, type of the starting materials, in terms of the powder characteristics, the packing densities, the chemical composition, and so on. The sintering variables have been extensively studied in terms of transition from a loosely packed powder to being able to form necks, reduction of pore size, final densification. The sintering variables include numerous aspects related to the composition, the additives, the chemistry, the use of pre-alloyed powders versus mixtures of components that constitute the alloy, types of powder form fabrication methods, size distribution, overall density and the existence of any density gradients, the heating rate, the atmosphere, time, temperature, cooling rate. Lot of sintering models exist and continue to get refined that provide a decent handle on the multi-physics problem involving sintering phenomena. In comparison, the process variables and their dependence upon the material characteristics, powders, in 3D printing is relatively less understood and provides a huge opportunity for research, for intellectual property, for being able to generate a competitive advantage, so on. Things that would allow for the field to advance. Sintering furnaces are important to understand. First of all, when you have a green body that's generated by 3D printing, followed which requires binder removal followed by sintering. And here's an example of a batch furnace that can be used. And in contrast, continuous furnaces can be loaded as well depending upon production volume. It is anticipated that for the bottleneck that is created by 3D printing processes, batch furnaces might be more likely used compared to continuous furnaces, at least for the near future.